Okay. So some of the administrative things first. You must have had your first lab on Thursday. The second lab is going to be on Monday. As we have already discussed, you are having multiple labs in 1 week, simply because to cover up for 1 or 2 labs which were missed. And also, your first midterm will be almost 70% consisting of, I mean, I'm not going to give an exact number, but approximately 70% on ARM architecture. And then rest 30% we'll be covering on implementation, which I plan to start from today. You are also going to have practice quiz. So the practice quiz, the first practice quiz which you are going to be given, you can take that exam anytime between this 24-hour period. But once you start, you have to finish it. I mean, you can't say that, okay, now I'll do rest of it after 2 hours or something. So once you start, the stop clock will start ticking down, and then you have to finish it. The first quiz is quite easy, and you are given much more time to solve than we would be giving in the exam. So for 20-25 questions, you are given. Can I request Mr. Vyom to turn off his mic? So you will be given 25 questions, and then you will be given 1 hour to solve it. You need to practice it to solve using the 3-page guide which is given to you, that is known as ARM Quick Reference. You are supposed to use only that. The question is whether it will be graded or not. Yes, of course it will be graded, but I don't propose to take the first couple of quiz into account for towards the final grade. But that doesn't mean you should take it any less seriously. You should rest assured that since the result of the first 2 quizzes are not going to be considered towards the final grade, so you can try to see your real potential, try to solve it, and then you will get an idea that how good you are or how much more effort you need to do. So don't copy, just try to solve it yourself. If you get less marks, it's okay, because this is, I mean, that is going to be a barometer for your own understanding. If your understanding is any less, you can start working on it. I propose to, I mean, this is still not fixed, but I propose to take one final quiz on Thursday before the exam. So I don't know which date would that be, but that Thursday's quiz, I plan to take towards, I mean, consider the grade of that towards the final grading. So as I discussed earlier, I do not wish that, just 2 exams should determine everyone's future. So probably, and I mean, I will still get back to you, but I mean, this is most probably, this is what's going to be, that I'll keep 1 exam on Thursday, for which you have to 15% of the total grade, and the second exam, which will be taken at the time of your midterm, that will be carrying 25% weightage. As of now, there is only midterm, but I propose to do this, and probably it is going to help those people who somehow don't manage to do well in one of the exam and lose a lot of big chunk of their grade just because of messing up one exam. Okay, so does anyone have any question regarding what I have told you just now? Okay, apparently there are no questions.
Sir.
So let me, yes.
Sir, in midterm, can we use that 3-page reference guide that you are given?
In midterm, you are not supposed to carry anything with you. So that 3-page guide, usually what they do is put it as a first question. And so that, you can jump between questions. So, I mean, if you want to refer to your 3-page guide, you can jump to first question, and first question is basically nothing but this 3-page guide. So yes, it will be given to you, but you are not supposed to carry it in a printed format. It will be part of the question paper.
Okay, thank you, sir.
Okay. So let us just finish. I told you one thing that, I wanted to finish the interrupt part before I start the implementation. So I hope you can see this. Can you see the PowerPoint slide?
No.
It is blank.
Okay, you can't see it.
Now it's visible, sir.
Now
it's visible, sir.
Okay,
now it is
great. So the last part which was not done.
Not
was-
visible again.
No, sir, not visible.
invisible.
Okay. Now let me do it again. Visible now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So in exception handler, there is a concept called vector table. So we have talked until now that, there are different types of interrupts and exceptions. So interrupts are like IRQ and FIQ, which usually comes from outside. So for your devices or your sensors or whatever you call it. And then there are certain internal things, that is like reset, data abort, prefetch abort, and then there is a software interrupt, and then there is undefined instruction. So these are the internal exceptions. And I told you there is a subtle difference between interrupt and exception, but we are going to use those two terms interchangeably, at least for the part of this course. So now, suppose a particular IRQ has come. So that means a normal interrupt request has come. So what is the methodology that your hardware will follow? So whenever an exception occurs, the first thing your hardware will do is copy the CPSR of your user mode into SPSR of whatever interrupt has caused. So if it is caused by IRQ, then CPSR of your user mode will be saved into SPSR of IRQ mode, right? That's the first thing which is done. Number two, it sets appropriate CPSR bits. So the first, this is important. All interrupt handlers are written in ARM instruction language. Even if you are using writing a program in thumb instruction set, but interrupt handlers are always an ARM instruction set. And that is to, make it slightly quicker. So if you are working in user state, you are working in thumb state, then, the T bit will be set to 0. So that means now you will be working on ARM state. So that is the first thing which is done. Second thing, mode bit is changed. So mode, which was user mode till now, will change into IRQ mode because IRQ interrupt has come. And then interrupt disable flags if appropriate. So if your IRQ is set, so now you have got one flag for IRQ and one flag for FIQ. If you set your FIQ, someone has said that, please share all your PPT. I will do that in today or tomorrow. I'm going to share my PPTs. But till then, the IRQ bits, FIQ bit, you cannot set it to 0. That means you can't disable FIQ. Why? Because FIQ is a VIP interrupt. It is allowed to come at any time and disturb your normal interrupt. So you don't set FIQ bit to 0. But if you are in IRQ, then it is up to you, your policy to decide whether another IRQ can disturb the current IRQ. So based on that, you will set your IRQ to 1 or 0. So that means that is up to the interrupt disable flags. Now maps in appropriate bank registers. So if it is IRQ, then from R0 to R12 will be saved to a stack, and using your STM instruction, it will all be saved. And then bank register R13 and R14, they will not be saved because that's where you have your link register and your stack pointer. You will save your PC return address to link register. Why? Because when you come back, when you are done with your interrupt handler and interrupt has been satisfied, you want to come back to your user program, and user program, wherever you have left, you want to start from that point. So basically you want to set your PC value to that particular point. The last one is then once it is done, you want to set your program counter. You want to bring it the address of the interrupt handler, right, to the program counter, because then program counter needs to know that now okay, my user program is gone. I have to service an interrupt handler, which is another program which is written in again ARM instruction set. But where is it? So to show where is it, the hardware will automatically bring in the address of the first of the program. But here's the trick. It is done in a rather indirect way. So how is it done? So as you can see, this is known as a vector table. And each interrupt handler is given exactly one word. So that means you can put only one instruction for, say, IRQ mode, then data abort, prefetch abort, software interrupt, and undefined instruction, and reset. Right? Each one is given only one word. Now you know pretty well that interrupt handler naturally has to be a big program, or at least a reasonable sized program. It can't be just a one-line program. So what happens is that first it puts in the table, say suppose it's IRQ, then it sets 0 hexadecimal, then so many zeros, then 18. That address is put into program counter. So the first instruction which is fetched is from here. Now this instruction, as you very well know, would be a branch instruction, or a jump instruction, or a move instruction, or something. That means this would be a pointer where to go, because the actual interrupt handler will be over here somewhere, or down here. If it is going down, then then interrupt handler will be written over here. But the first address, the vector table, is over here. So that means this particular instruction, which is connected with your IRQ handler, will have a branch instruction necessarily. It would jump to wherever it is. It will go here, some address, and then whole program would be written over there. Same thing for data abort. Whenever data abort exception is there taken, then this particular address will be put into your program counter. Then your program counter will fetch this particular instruction which is associated with data abort mode. And that instruction again is going to be a branch instruction, right? Why? Because your program has to be at least some number of lines long, and this is just one line, so it will go somewhere wherever that is down here and start executing. And so is true for any other interrupt. The only exception is made for FIQ. Someone has asked what is CPSR and what is SPSR. I think I've told you last time that CPSR is current program status register. So this is your CPSR, and these are the flags. This is the mode address, and these are the bits. So this is like a snapshot of what your program is doing. And these bits are reserved. So I mean, they are not found out any use for it right now, but whenever expansion takes place, they may use it for some appropriate reason. So this is the CPSR. And when you want to save it, you call it SPSR, that is saved program status register. And this is current program status register. So basically this is PSR, but you know, when it is currently being used, you call it CPSR. And when it is saved somewhere, you call it SPSR. Okay, now moving on. As I was telling you that FIQ is different. For FIQ, as you will see, it is written at the bottom. And you know, your memory is growing this way. So whenever the FIQ interrupt is there, your CPSR will change the mode to FIQ mode. And this particular address, hexadecimal address, so many zeros and 1C, will be put into program counter. Here, the first instruction will not be a branch instruction or a move instruction or a jump instruction. Because FIQ is a VIP, this is the interrupt handler will start right from here and it will grow down. So once again, why it is done like that? Because the FIQ is a VIP and you don't want to waste time in jumping and finding address and going there. So FIQ interrupt handler will start right from here. This is important. Remember that FIQ interrupt handler, the first instruction is not necessarily a branch instruction or a jump instruction or a move instruction. Whereas for all the rest, it's either branch, jump, because you know the actual program will start somewhere down here in the memory space. Whereas FIQ interrupt handler will start right from this address and will grow downwards depending on how many instructions are there. Is this all clear?
Sir, how would it come back to the main program?
Okay, so this is the return thing. When it is done, the message will go to the hardware and hardware will do the reverse thing. So first it will do is, we took the example of IRQ. So now this is the opposite of this would to happen. So that means you save the CPSR of your user program into SPSR of IRQ. Once it is exception handler is done, the exception handler is to finish this part before giving the chance to others. So that means it will, whatever was saved in SPSR of IRQ will be put again into CPSR. So that means now the user mode CPSR is back. Second, restore PC from LR. So that means now you are back to your program status. You know, the program left at certain PC value. Now you are restoring it. It will also restore, again, you know, the thumb state or arm state. Whatever your user program was in thumb state, it would change it to back to thumb state. The mode, which was this mode bits, which were in IRQ, will again be changed to user mode state. And then, you know, this would have already been changed now because now CPSR of user is back. So, I mean, this flags are restored. And so that means now you are okay and, you know, you can start working. And of course, most important thing is to bring back the values of R0 to R12, which is stored in your stack, to bring it back to registers. Right, so that means all your registers of the user mode are back. 13 and 14 were not overwritten. So now you are comfortably back and the status is restored just as it was before when you were in the user mode. Any questions in this before we move to a new topic?
Sir, but if an exception requires termination of the program, then why will it return back to the user program?
Okay, good question. So suppose if you have a reset or, you know, if you have a termination, then, you know, those conditions would be given and, you know, your program would terminate. But what I'm saying is that, you know, suppose there is a solution. See, most of the time, the interrupts usually which are taken are IRQ, FIQ, and software interrupt. Right? These are the three interrupts which normally comes. FIQ and IRQ, you know, they are connected to sensors or, you know, devices or say keyboard and mouse. So IRQ and FIQ are taken very often. software interrupts are usually, debugger or something. So, it is like, it will tell you the state of this program. It will just step through the program and, giving you intermediate values. So that is also very common. Whereas the interrupts like reset, undefined instruction, prefetch abort, and data abort usually will not occur unless, you have made some serious error on porting and, you don't know, or undefined instruction is like, you're tried to play clever and given some instruction, which is, you've defined your own instruction and given it to the client. So only in those times, your program would terminate. But, for most of the interrupt and exception, which are three, like IRQ, FIQ, and software interrupt, most definitely your program will come back to your user program state. Does that answer your question?
Yes, sir. Thank you, sir.
Okay. So now I will go to a new and interesting topic. This topic is on implementation, and it will create a lot of questions in your mind and also answer them in this particular session. So let me Can you see the slide of implementation issues?
Yes, sir.
Yes, sir.
Okay. So now, as the title of this slide very clearly suggests, we are going to talk about implementation issues. And here we are going to talk about the terms pipelining and hazards. Now let me just take back you to the first class or the first lecture when I said that, then there are two views. One is the programmer's view and the second is implementation view. Now the programmer does not care what is under the hood. So like when I'm using my laptop, I don't know what kind of processor is there inside or how it is solving my problem or how my program goes in and, it is getting executed and, the answer is coming out. All I'm interested in is I'm giving my program, C program or assembly language program as input. And then, I want the correct output. How you arrive from beginning to end is not a programmer's concern, but it is definitely an implementation person's concern. And it is also very much an informed programmer's concern, because if you want to be a good programmer, then you want to write a program which would be helpful to your architecture. So all of you should pay heed to this implementation issues, because anyone even with a BSc background can write a program in C, right? Then what's the difference between an engineer and say a person with a BA degree or BSc degree or BCA degree? If you want to be a real good programmer, then you need to know about the implementation issues, and you need to understand what pipelining means and what your processor can offer, or how can I write a program which can help my processor work faster. And second one, which is very, very important, and that is known as power-aware programming. And I will keep on reminding you at each and every step whenever the time comes that this is how you can save power while execution. Where does so that means you don't want unnecessary memory references, because making memory references take up power. Of course, it takes up time, but what people or computer science people were not concerned with or not aware of was that power is also an important factor. And very recently, with the advent of handheld devices, computer science people are slowly becoming aware of that okay, power is also an important budget quantity, that I've got limited power budget, And if my instructions which I given is taking up too much power, then probably I would write my program in a different way. So let us start in a new way. Now, look at this. This is a kind of a marketing jargon which is promoted by ARM. But right now, this may sound like gobbledygook to you, but at the end of this course, you will understand each and every word of this particular sentence. So the purpose of this course will be served if you can make sense of sentence like this. So what it says is that Cortex A77, well, A77 is the model name, is a 13-stage pipelined, complex, 6-way superscalar out-of-order processor with a 10-issue backend. It has 10-cycle branch misprediction penalty. So at the moment, when you start off, this may sound like, okay, I mean, what does this even mean? We will discuss what this means as time comes. And, at the end of this course, you can read this very knowledgeably, or any sentence like this, which is written for any other processor, you can make sense of it and make a judgment whether it is good or bad. Okay. So this is for Snapdragon 855, I believe. Okay. So now computer architecture has got two parts. One is instruction set architecture, which you guys are studying, and we have just finished that part of the course. That is, one is instruction set architecture, which has got, how many registers are there, and then how many interrupt, what is the interrupt model like, how many types of instructions are there, and memory, how much memory is there and where is it. That's all instruction set architecture. And second one is implementation, which we are going to study starting from today. Then comes compiler. So it would start, how to make program better. We'll see that, your Kyle compiler will make your program in such a way, it will make changes to your program. This might be a little disconcerting to you, that you have written a program in a certain way and, you're allowing the compiler to change it. Then, you may feel that, what about the correctness of my program if a compiler is allowed to change some of the instructions, order of the instructions. Well, we are going to study some of this and see how things are done in a better way. Second is register allocation. Now, as I told you, register is a very, very precious commodity. The reason for that is that register access is very fast. Why? Because it is part of the processor. So whatever the data or instruction, usually data, is stored in a register, that can be accessed very quickly. So you are supposed to store only those variables which are going to be used very often, so that you don't have to go to memory, which is outside the processor, and then bring back the data in there. So even without knowing, you can say, okay, if I'm executing a loop, I would like to put my counter, that value of the counter into a register, so that, I don't have to go and access it after every 5 instructions or every 4 instructions. So I'll keep it there. So that kind of register allocation, it will be decided by your compilers. This optimization, we will see some of these things later. And then, there is operating system and software technique, which you are going to study in a different course, which will be coming probably later in the next semester or next year, probably next semester. Okay. So initially, when someone asked a question, then, I had to do this. There is a difference between non-pipeline processor and pipeline processor. So most of the people in Gujarat, and in fact, in most of the places in India, they are studying Intel 8085 or 8086 processor, which was like developed 40, 50 years ago. But then, the faculty members are comfortable with it. They studied from their professor and their professor studied from someone else. So it keeps on coming. But, that thing is now passé. because hardly any processor worth its value is a non-pipeline processor. Almost all the processor, even the tiniest one, at least it has got two-stage pipeline. So now let us see what is the purpose of having a pipeline. So as I told you, the idea of pipeline came from Henry Ford. So Henry Ford was, of course, he's making cars, and he saw that, or he observed that suppose there are 5 teams making a car. So one team is, say, fixing up a chassis. The second team is putting in engine. The third team is doing electrical wiring. The fourth team is putting upholstery and other things. And the fifth team is painting. So he thought that, at any time, only one of the team is working. Right? When, someone is building a chassis, the other teams were just hanging around. So as soon as the chassis people are done, then they will move to one side and sit down, and the other team will come and start working. So they say it's a total waste of time. And, a car, suppose it takes like, maybe 20 hours end to end. Each team is going to take 4 hours, just suppose. And he said, let me just decide and change it into, say, 5 parts. So first station, chassis, formation of chassis. The second one, engine fitting. Third one, electrical fitting. Fourth one, upholstery. Fifth one, painting. So, and each one is always busy because as soon as the chassis people are done making the chassis, they would pass on the chassis to the next station, which is like engine fitting, and then again they will start making a new chassis. So here also, making of one car from end to end will also take the same time, 20 hours, because first one will finish the work, pass it on, and then they will do something else, and then pass it on to this. So in fact, it may take even little more than 20 hours because it takes some finite amount of time to lift that chassis from here and put it to the engine people, and then engine people will pass it on to I don't know, upholstery people, and then electrical wiring people and upholstery people and painting. So for one car to come in here and come out at the other hand will almost take the same time as a non-pipeline processor. Then you may ask, what is the advantage? And this is the advantage, and I'll tell you. See here, suppose each car is taking, say, 20 hours to finish. The first car will come out after 20 hours, second car will come out after another 20 hours, third car will come out after another 20 hours, so on and so forth. Whereas here, once all the stages are filled, the first car will come out after 20 hours, but the second car will come out after just 4 hours. Why? Because, then, it is just time taken by each thing. And then, after every 4 hours, you will get a car. This is a very important conceptual point, and this is the advantage of assembly line. And that's why all world's manufacturing processes, plants, they are using this assembly line technique. So the same technique is used by a processor, that, one instruction is being like, fetched. At the same time, here some instruction is being decoded. Here some instruction is being executed. This is memory access stage. So load and store instructions are accessing memory. And this is write back. So that means the result is being written back into a register file. And then it is coming out. So at every stage, some instruction is there. So once the pipeline is filled, that means there is one instruction in each stage. The first instruction, the original instruction which went in first, and you may call it the 0th instruction, may take, I don't know, let's use nanoseconds here. It may take, say, an example which I have given is, say, 17 nanoseconds. So the first one will come out after 17 into 5 is 85 nanoseconds. But the second instruction will come out after 85 plus 17, that means 102 nanoseconds. The third one will come after 119 nanoseconds. Whereas here, there is no difference. First instruction after 75, second instruction after 150, third instruction after 225. So now you can see the advantage over here. That is the difference between latency and throughput. Latency is time taken for any given instruction to go in from here and come out at the end is known as latency. Whereas throughput means for in a given second or a given minute or a given hour, usually we take seconds. So in a given second, how many instructions are coming out? That is known as throughput. So be very clear about these two terms. Latency means for an instruction which is entering in the fetch stage, that's the first stage, from that time to the time it actually comes out. That means after the results are written into register file. That is known as latency. So I will make a statement that, you may say that, you have made this 5 pipeline stages. What if you divide up the work into 10 pipeline stages? Wouldn't your throughput be even more? Well, theoretically, yes. If I divide my work instead of in just 5 parts, I divide my work into 10 parts, my throughput will be doubled, right? So now, instead of coming at every 17 nanoseconds, now it will come out at every 8.5 nanoseconds if I have 10 such stages. If I make 20 stages, then it would still be reduced. I mean, divide this by 4 and that much throughput will be there. I will make a statement like this. If I increase the pipeline stages, the latency may increase. And why it may increase? Because I said, it takes finite amount of time to shift something from here to here. And the reason for that is that, these 2 stages in a processor or any electronic machine, you make a stages by putting a flip-flop. Like you put combination logic on one side, then divide it up with flip-flop. That is a sequential logic. Then again, a lot of combination logic and sequential logic. So it would be something like this. So this pipeline stages, if you want to know from DLD a point of view, rather than, just a computer science point of view, it would be like this. Okay, so I have drawn something like this. This is my conceptual drawing, what a computer science person would draw. This is fetch, decode, execute. Remember these words, we'll be using n number of times, so you should know what each one means. This is memory, and basically memory, actually it is data memory, but we just write as memory. And then this is write back. So that means writing into register file. If you want to write like a DLD person, then you would say fetch would have, say, a lot of combinational logic. And, I'm just drawing a cloud and I'm saying this is combinational logic. And it has got some input here, and then, it is passing through lots of gates, which you have made a circuit. Then between 2 stages, I will have a flip-flop. In fact, I will have several flip-flops, but I'm just drawing a conceptual thing. So I'll do a flip-flop, and then there is a clock which is coming in, and then I will have another combinational logic for decode, and then it will again go through some flip-flop, and that is also connected to clock. And then, you can draw other combination logic clouds and flip-flops and others. So let me, for example, say, let me just go up to this point. See, this flip-flop is like a gate which opens only at the rising edge of the clock. Well, I mean, it can also open on the falling edge of the clock, but then, I'm just assuming that, this flip-flop is made in such a way that, when my clock edge rises, at these edges, my flip-flop would open. So this combination logic has to finish its work in this much amount of time. In fact, it has to finish a little early because you know about setup time and hold time in a flip-flop, so that you have to allow the data to settle so that it can be correctly latched into a flip-flop. So it has got slightly less than this much amount of clock period. So if you are using a 1 gigahertz processor, that means your time period is 1 nanosecond, right? So you've got 1 nanosecond time for this cloud to finish its work. In fact, less than 1 nanosecond, because you have to consider setup time and hold time on both sides. So this is how it is going to work, and your fetch at certain amount of time it will go to decode, then it will latched over here, and then in the next cycle it will go to execute, so on and so forth. So like a train, it will keep on moving. Is this conceptually clear to you, the whole purpose of pipelining and how to implement it? Okay, so I believe you have understood. Now, we have posed a second question. And the second question is, how many pipeline stages should one make? So let us just say, for a simple processor with no pipeline stages, so say no pipeline, so that is just like a one big blob. This is no pipeline, and it is taking, say, 100 nanoseconds, right? So at every 100 nanosecond, one instruction is executed. And then, I make a processor, which is, I divide it into 5 parts, the same one, but, I divide the work into 5 stages. And each one is taking, say, 20 nanoseconds. So my latency is remained the same. For instruction to come in here and come out here, it will still take 100. As I told you, it may take little more than 100 because there is a time which is latching, and so setup time, hold time you have to add into it. But for theoretical understanding, let us forget about it. So you say latency is 100, but now my throughput is like every 20 nanoseconds. Once the pipeline is filled, that is important sentence. So then, you may ask a question, then why don't you divide the work into 10 parts? So then, okay, I divide it into 10 parts, and then, this is the first part, and this is the 10th part, and each one is taking 10 nanoseconds. So you'll say that, my output is like every 10 nanoseconds. Then, suppose if I say, how about 100 parts? So let's say this is your first stage, and this is your 100th stage. And your throughput is every 1 nanosecond. So, now you are going faster and faster. This is called 1 gigahertz processor. Because why? Because you are getting throughput every 1 nanosecond. You must always remember that frequency is equal to 1 over time period. So if I say 1 gigahertz, then time period is 1 over 10 raised to 9. That means 1 nanosecond. right? So I mean, this you should always remember. So that means it is becoming faster and faster. So a mathematician among you may say that why not have infinite number of stages? If you have infinite number of stages, then your work will be done in 0 time, right? So as soon as you enter, you will get an output. So then, the question is that, yes, theoretically it sounds, feasible that, why not have 100-stage pipeline or 1,000-stage pipeline processor or 10,000-stage pipeline processor. Why? Because it will make your work very fast. Then, if I tell you that most of the processors at most have like, even the fastest one are like 10 stages, 15 stages. Some of the Intel processors are 20 stages, but that is max. So I mean, that is the maximum amount of stages the work is being divided into. Your microcontroller are like starting from 2-stage to 3-stage to 5-stage. I mean, that is about it for microcontroller. And for application processor and for servers and others, at most it is around 10 to 20 stages. So then you think that, then what's wrong? My mathematical understanding says that, more the number of stages, then mathematically I can get better and better results. But the problem which you are going to study in a very short time is that you will be wasting also a lot of time. Whenever there is a branch, you will be wasting a lot of time because, you will have to recover from your prediction. Now, you will not make sense of the statement which I just made that, how am I going to waste time? Then, just wait for this lecture to finish and then you will immediately start making the connection that, why I would be wasting time. But at the moment, I want you to have this idea in your head that theoretically it is very good to have large number of pipeline stages and divide up the work into that many number of stages so that your throughput is more. Latency will remain the same or it would increase, but then throughput would also increase. And you are worried more about throughput, you are not that worried about latency. If latency increases by a little bit here and there, you don't care. So to come back to this point, that first of all, why there are not too many stages, the reason which you can understand at this moment, some of the reasons I can tell you is that, it is not easy to divide up the work in equal amount. So for example, I change just one thing. I have got pipeline stages, but I have divided up my work in something like this. So my work is divided in a way like this, that this first stage is taking 10 nanoseconds. The second stage is again taking 10 nanoseconds. Any question? Third stage is taking 30 nanoseconds. Fourth stage is taking 5 nanoseconds. And 15 nanoseconds. And the final one is taking 35 nanoseconds. Right? So now, I mean, this is because, I have problem balancing the load because, some stages you may feel that, it is not easy to divide up the logic. So something has to be done in one part. So, unfortunately, all my stages are not of equal 20 nanoseconds each. But, they have become like this, that, I have the first one 10 nanoseconds, it is working too fast. Second one is 10 nanoseconds. The third one is 30 nanoseconds. The fourth one is 15 nanoseconds. And fifth one is 35 nanoseconds. So Latency wise, I have no problem. It is still taking 100 nanoseconds, just like here. But what would be my output? So once all the stages are filled, after what time I will be getting an output? Will I be getting output at every 10 nanoseconds? Will I be getting an output after every 30 nanoseconds? 15 nanoseconds?
every
Or
35
35
nanoseconds.
nanoseconds?
35 nanoseconds.
Okay, anyone else? I'm sorry?
Maximum of all. 35 minutes.
Okay. So here the thing is that whichever stage takes maximum amount of time, that will determine your throughput, not the one which takes minimum amount of time, right? Because this stages may finish work in 10 nanosecond, but then once it gives up to here, it will not be able to move forward every 10 nanoseconds. Why? Because there is nothing to give, because this stage is busy, so it says I'm not ready to accept your data. And because this stage is saying I'm not ready to accept your data, this stage will also tell this stage that I'm not ready to accept your data. So I have to stall till this stage is ready to accept my data. Both of these guys will have to sit without doing any work, right? And then here, this is the biggest block. So that, this is going to be the roadblock. And that's why the maximum throughput you will get is one instruction execution after every 35 nanoseconds. So just as they say that the chain is as strong as the weakest link, same way your processor is as fast as your slowest stage. So that is the reason why people say that all the stages should be well balanced or perfectly balanced. I mean, it's easier said than done. It is very easy for me to write 20 nanoseconds everywhere and say, okay, this is a perfectly balanced stage. So, throughput would be every 20 nanoseconds. But in real life, it is not that easy to balance the stages. So if you are not able to balance the stages properly, and even if you increase this to double, but if one stage is taking too much time, then, it would be as slow as your 5-stage pipeline. So that is one of the reasons which you could understand at this point that why you are not increasing the number of stages to a very high value. The second one which you would understand when you study the effect of branches on the performance of a program, at that time you will immediately say that, okay, now I understand why pipelines are not too long. Otherwise, it would create a havoc. Does anyone have any question up to this point?
Yes, sir. I have a doubt that you told that it is not easy to balance. So, what are the factors that affect balance of these stages?
Well, I mean, it's kind of a very involved questions, which is like into dividing up the work. So, for example, after all, the most complicated processor is nothing but made up of interconnection of several NAND gates, NOR gates, AND gates, OR gates, or you can design the most complicated processor using only NAND and NOR gate, right? Even your topmost Intel Xeon Phi server level chip or Apple M1, you can design using just 2 types of gates. But then you're dividing up the work and storing it in a certain place, and so that each work is quantified as a 10 nanosecond or equal amount of work. That is not very easy to define. And there are various technological reasons that which you can't do that, because in certain things result is dependent on something. So certain quantum of work has to be done in one shot, and that one cannot be divided into 2 parts because results are interdependent. So that's why you cannot very easily slice everything just as per your needs. Sometimes some stages, unfortunately, have to be larger. I mean, you will understand it when you actually start designing this.
Yes, sir. I got it. Thanks.
Okay.
Sir,
Yes.
sir, even if we divide in equals, but it is not a case that for every program this partition are consecutive partition partition of processor are taking same amount of time. So it is also dependent on program that how much one stage will take time.
No, that is not correct. I will tell you why. See, after all programs are finally converted into instructions. If it is ARM-based process, then it's converted into ARM instruction. It is Intel processor, then it's converted into Intel instruction. But in any RISC-based processor, each instruction has to go through fetch, decode, execute, memory access, and write back. Right. So these are the 5 stages, and you are supposed to guarantee that each instruction will pass each stage in one cycle. So, one cycle could be 10 nanoseconds, so that means 100 megahertz processor, or, depending on, what your maximum is, then, you determine the cycle time. So that much amount of thing, all those basic instructions. So if you're designing a processor which is compliant to ARM instruction set 4T, then all 56 instructions has to pass through these 5 pipeline stages, and each stage should be done in one cycle. Now, one cycle could be, if you are designing a 100 megahertz processor, then one cycle is 10 nanosecond long. Then each one should be more or less 10 nanoseconds. Right. So the program, might be a 10,000 line long program with lots of loops and other things. It doesn't matter, because finally, if you break it down to the basic Lego pieces, they are instructions. So, there are 56 instructions. Or if you go to a very high architecture like ARM version 9 or ARM version 8, it might have 600 instructions, but each instruction is guaranteed to finish each stage in one cycle. Does it answer your question?
Yes, sir.
Okay, it seems like you have still some doubt, but your doubt might start clearing as we go deeper into the implementation issues. Okay, so this is how your instruction will be done. From now onwards, we'll concentrate on 5-stage pipeline, because it's also explained in your book in the same way. So we'll keep it that way. So the first stage, its job is only one. It has to go to instruction memory, fetch an instruction, and bring it over here. That's it. Then when the clock allows it, or the flip-flop allows that instruction to pass through, it will come into decode. In the decode, it will do 2 things. First of all, I'm not talking about, decoding of thumb into ARM, and then, that is also done, but it is not given over here. But you can assume if it is thumb, then it will be inflated into an ARM instruction somewhere over here. But let's assume it is just ARM instruction. First thing is, you would decode what kind of instruction it is, right? So you will make sense of the opcode which is given. So what does opcode say? Does this opcode means add? Does this opcode mean subtract? Does this opcode means a branch instruction? So that it would figure out. And then, you will have something which is known as control circuitry. Control circuitry will pass on the message to ALU, that's what you are supposed to do. Now, learn an important lesson over here. What we are showing here, or what we'll do in this particular class, is only study of the data path, that how data will move. The second, which is important thing for implementation engineers, is the control path, and that is much more complicated. That would have been done if we had done, actual design of using Verilog, and then, you have to design control signals that, suppose if my decode circuitry has figured out that this is an add instruction. So what kind of message will go from here to ALU, and, force ALU to perform add operation for instruction, which is just coming in. So those things are known as control circuitry, and that we are not going to study in this particular course. If you want to know more about it, then, you look at the Patterson and Hennessy book, the hardware software approach, and that would explain you in an excellent way how to design control circuitry. But as a part of this course, we are just going to see how the data is flowing, not how the control is flowing. So as I said, in this part, it will figure out what kind of instruction it is. And then, suppose it is say add R1, R2, then it will figure out it has to read register R2 and R3 from register file, which is somewhere over here, and pass on that values to your ALU as input. Now ALU will say, okay, I have this add instruction. The idea is message has already come that, I'm supposed to do add operation on these two operands of say register sent from register R2 and some from register R3. I will add it. The answer will come out, and then, it will pass through memory access stage. Now, as I told you earlier at that time, during the first or second lecture, the memory access stage will be used only by load and store instruction, because only two instructions can access data memory. All other instruction will come and go out. It will just spend 1 nanosecond inside. So it's like they are sent in a room, asked to sit for 1 nanosecond and then leave. So they are not doing any work. They are just coming there, parking themselves and leaving when this gate is open. And in this stage, it will again go to register file and the value of R1 would be written into it. So the decode part reads the register file, and the write part actually writes into register file. Is this clear? So this is how your instructions or your programs will flow through, and programs will come one after the other as the PC value suggests. So fetch will keep on fetching whatever the PC program counter suggests. Now you have got some issues here. See, every time if you are able to bring in one instruction at a time, that is the most ideal thing. Remember, always remember this line which I have written. Pipelining is a great idea as long as we manage to keep it filled. It is not always possible to send one instruction every cycle. And you will see why. And these are the reasons that the data flow will cause a problem, or there will be limitation of resources, or there is going to be branches, so that you will not be able to push in one instruction after the other. If you have written a nice program which doesn't have any of these issues, which does not have branches, it does not have any limitation of resources, or instructions are not bothering each other, then you will get cycles per instruction of 1. So like, we were saying very briefly that, at every one, if suppose these are all 10 nanoseconds, then every 10 nanosecond, one instruction will come out. So that means it is known as cycles per instruction is 1. That means at every cycle. So suppose if your frequency is 1 gigahertz, then your cycle is 1 nanosecond, right? Cycle is time period. So every 1 nanosecond, you will get one instruction out. And that is the most ideal thing. And that is known as CPI, cycles per instruction of 1, that each instruction will take 1 cycle. And that is what the founding principle of your RISC processor is, that every cycle or each instruction should take only 1 cycle to execute. But because of this, your CPI would start going up, and it may go up to 1.5 or 1.7. And why it would go to that value? It is because of this 3 things. Now you may ask one thing that, can I write my programs in a better way so that, I don't have any of these issues? That is number 1. Or can I make some changes in the hardware so that, these issues are not bothering me? Well, we'll see. And in fact, the problem which you are going to see in next 10 minutes, which is remaining in this thing, that will suddenly set you thinking the way you are writing your program in Kyle compiler. Now, the first is known as dependency. The first one is data dependency. Now, let us say that, you very simply write a program like this, add R1, R2, R3, right? This is the first line of your program. And second line of your program, you say subtract R4, R1, R3. Now, as a programmer, there is nothing wrong in this. Right? As a program goes, there's two correct instructions, one after the other. What's wrong in it? But, from an implementation engineer, this is going to cause a major problem if you don't pay attention or if you don't find out a way to solve it. Right? So you may never have worried about these things, but as an implementation engineer, this should start ringing alarm bells. And this is known as dependency. So what is the dependency here? Here, instruction number I is creating a value in register R1, correct? And the second instruction, which is immediately following it, wants to read the value of register R1. Now, it should not happen that R1 should read a value of R1, which is set by an instruction which is older than I. That means previous instructions previous to I. That will cause a disaster in your program. And how would that cause? So let us take a look at here. See, these are the two instructions which we were just talking about: add R1, R2, R3, and subtract R4, R1, R3. Now here, the value of R1 would be written into a register file only in this cycle, right? The register write. Okay, that's fair because that's how we have designed it. But the second instruction, it would say I need to read registers R1 and R3 at this particular stage, right? Because I have to give it to ALU. So that means it will say I need to go to register file and read the value of R1. But if you allow it to go to register file and read the value of R1, that would be an outdated value. It would not be this value of R1 which you want. You see the problem. So this is going to cause a disaster to your program. Your whole processor will go. Nobody would buy your processor. So you must never have thought about these dependencies when you write your program, and rightly so. That why should a programmer worry about it? A designer has to take care of everything. So you as a designer will start, scratching your head that, this is going to be a disaster. If anyone uses my processor, and if I don't give any recourse, then, this will cause a problem because, it will give you wrong result. So what should I do? The simplest way would be you should stop execution of the second instruction. That means stop the pipeline, not allow any new instructions to come in. Stop this instruction in this particular stage and say not allow it to move forward till this instruction. See, sorry, this is just one cycle late. When this instruction wants it, the value is in this and the value of R1 is here. It is not yet written. Then when it comes here, theoretically, at that time, it will be in register write file, and then, it will be written. But, you can't allow that to happen. So you will have to stop this instruction J, that is sub R4, R1, R3, into this stage. So that means rest of the instruction, the whole pipeline is stalled. You are not allowing any new instructions to come in. Why? Because, this instruction would say, I cannot move forward till the correct value of R1 is written. And that is known as raw hazard. Now there are two things. This is raw means read after write. So that means reading of R1 should be done only after writing of this value of R1. If you don't follow it, it is going to cause a problem. Now there are two things which you again get into your head. There are two different terms: dependency and hazard. If these two instructions are, say, there are 5 instructions in between these two, right? Then, yes, there is a dependency between I and J, but it is not going to cause a hazard. Why? Because by the time this instruction number J, which is, say, way down here, when it comes into decode part, the value of R1 would already have been written into register file. So it can read. So that is known as dependency. Okay. But dependency will convert it into hazard only when they are one after the other. Now, this sentence is also not a gospel truth. Why it is not a gospel truth? It will depend on the structure of this pipelining, that how many pipeline stages are there. These two instructions, one after the other, are going to cause a problem in a 5-stage pipeline. But it will not cause a problem in 3-stage pipeline when first 3 tasks are done by a first stage and these 2 tasks are done by the second stage. And I will show you a little later on. So here's a very important point. And this, before closing, I want to get it very clear in your head. We talked about the major topic is data hazard. That data is going to cause a problem. Within the data hazard, the first hazard is known as raw hazard. Raw means read after write. You have to make sure that reading is done only after writing with the previous instruction. So R1 value has to be written first. Only after that you can read the value of R1 for the next instruction. So that is data dependency. Now, dependency can be converted into hazard depending on the structure of the pipeline. In 5-stage pipeline, it is definitely going to create a hazard. But if I divide this up into 2 stages, that this and this forms one stage and this forms another stage, then you can check for yourself. It is not going to cause any problem, right? So dependency converting into a hazard is machine property, or the implementation property. Dependency is a property of a way you write a program. There might be dependency between first instruction and 100th instruction. There might be dependency between 5th instruction and 200th instruction. But not all dependencies are going to cause a hazard. Only in certain conditions, the dependencies are going to be converted into a hazard depending on the structure of the pipeline. So in the 5-stage pipeline, if these 2 are written one after the other, they are going to cause a hazard. But if I convert this into a 2-stage pipeline, that this is the first stage and this is the second stage, same thing here, then you can check for yourself. It is not going to cause any problem. Is this concept clear to you? Because this is a very important concept.
Yes, sir.
Okay, so in next class, in Wednesday's class, I will just go over this again. In the meantime, please prepare for your quiz, prepare for your, do your assignments on time, and we'll meet again on Wednesday.
Sir,
yes.
In which chapter this new topic is being available? Means
it is given in the first page. It is given in the books by Patterson and Hennessy. You can refer to it if you like, but don't blame me if you find the language slightly tough on the first reading. So my recommendation to you is listen to my lecture thoroughly and then read Patterson and Hennessy. If you don't read each and every word of it, then don't blame yourself, because though as I told you, it is considered as the world standard book of computer architecture, but just because it is world standard book, you may have little problem understanding it. So you may have to read it 2-3 times to actually get the value. And if you get it from that book, no one is better than you.
and sir, what is the difference between move and load? Means I am having issue in understanding the difference between these two while doing the lab.
Okay, so load instruction, there are 2. One, are you talking about a pseudo instruction?
Sir, MOV move and LDR load, through which we get the loaded register values.
The load instruction is usually used to take a value from the memory location and putting it into a given register. So now the value of, the address of that memory usually has to be in some other register location. And the load instruction may play around with the address that, it say, okay, the address of the memory location where I want to get the value and put it into, say, register R1 is like, the memory address is partly given in R2, but you left shift it by 2 bits plus add 10 to it, and that is the actual address. So that is load instruction, whereas move instruction you can immediately move values if needed into a given register. Then you can also move your PC to LR. So there are certain things which are done by move instructions which cannot be done by load instruction.